Okay, hello. Today we are going to be talking about organizational network analysis. And I'm just going to talk through my R script, the outputs, all that, you know this. Okay, so just a little bit about organizational network analysis, which I will refer to as ONA from here on out. It's basically a method for studying communication and networks within an organization. So you can look at statistical models. Penelope, seriously? Stop being a brat. You can create statistical models, graphical models of people, tasks, group, pretty much anything within an organizational system. Social network analysis, which I think is like a form of ONA. I'm not sure right now. It's the study of structure, so it involves relational data sets. Structure is going to be derived from the from the patterns of relationships, like regularities within those patterns. So I think it is the same. I think those are interchangeable terms, actually, now that I'm thinking about it. This can be people, groups, or organizations. Okay, so those are basically the same. It's quantitative, but as we talked about in class, data collection is usually qualitative in nature. So that's one thing that can differentiate it from other types. Actors are network members that are distinct individuals. So for example, like employees within an organization, or they can be collective units. So for example, project teams within an organization. Relational ties, which we will see are the lines between actors within a network, can be informal. So, for example, whether people on one team know people in another team, or they can be formal. For example, whether one team is over another team. Actors can have multiple ties with other actors. This is known as multiplexity. So there's tons of terms that we talked about in class. So those are pretty much the benefits of ONA. So really the visualization of that, and you can figure out several different things from it. Where is information coming from? Who is like the main source of information? I'll go through some of those for my example. There are also problems with ONA. Like we talked about in class, it's very perceptual and subjective. So people are going to disagree on what the target value is a lot of the time. The data is based on perceptions. This is often true with qualitative data anyways, and really quantitative too, but the data collection method is really important to this type of analysis. So like unlike with CHAID, the struggle here is going to be figuring out what to do with the information that you're giving. So like we talked about in class, it's a tool. It's not necessarily a conclusion. So those are some of the weaknesses and challenges that you'll face doing an organizational network analysis. So I'm going to begin mine. So I have two data sets here, and one of them represents a list of employees on a team, like within a department. Their gender, which actually turned out like not to be relevant, but it was still just like data collected, and turnover, whether or not they turned over. And then here's a list of those same employees and projects that they worked on. So we have 3 projects here. So to begin, the iGraph package is basically the default package for network analysis. This is going to allow you to actually visualize. And like I said, I already went over this part, so I won't repeat that. Here I'm just going to attach the data. Okay, so a little bit more about like the background on the data. What I'm going to try to do here is make connections between people based on the variables within my data. An organization is having issues with turnover. Interviews were then conducted with employees with the company as well as employees who ended up leaving the company. The data here are taken from a project team within the organization whose department is experiencing especially high turnover. So what I'm looking for in this data is who has worked together with who and on what projects. This is because the interviews revealed that there were issues within certain projects that might have had effects on attitudes and turnover intention. So data such as who works with whom was collected during the interviews as well. Okay, here I'm just going to factor out my data. The text to the left of the arrow is what the variable is going to be called, like in R and within the syntax hereforth. And then henceforth? I don't know if that hereforth is a word, probably not. The text in parentheses is, to the right is the variable that R is going to pull the data from within Excel. So here we have the names of the actual variables in the data set. And here we have like whatever the shorthand is going to be. And this tells, this factor command tells R to factor this data in this way and tells it to name it that. So running that, okay, that went well. So visualizing the network. So step 1 is going to be to build a network using the iGraph object. So just describe the syntax. The graph.data.frame is the function that contains iGraph in order to create the object from the data frames. The D variable is going to take the edges connecting the actor nodes that are listed in the project's data frame, specifically. The vertices variable is going to require one column of node identifiers, which in this case is going to be the employees' names. This command takes the nodes that are listed in the turnover data frame and basically like connects it. So the vertices are going to be turnover, the nodes are going to be the projects. The additional columns in the turnover and projects data frames give other identifying variables to the edges and nodes, respectively. The false argument is because the network is undirected. This is because several employees worked on several different projects together, so that means that it's an undirected network. What I'm about to do is going to allow me to visualize the network without any additional information. So this is a very bare bones look. So first creating the network, and then this is actually the plot function is going to allow us to actually visualize that network. Okay, so here we have a very basic visualization that gives us information about who is connected to whom within this team or department. Each line represents a connection from one person to another based on what project they worked on together, which was specified in the syntax that I described above. So we see each of these lines, again, represents a connection. So this is pretty simple. Like Egger is connected to Williams and connected to Sammons. And then Williams and Sammons are connected to each other. And then Williams and Peterson, and so on. Other graphing variables can be used, though, to do more with the visualization. So the next thing that I'm going to do is color code the links to see which projects employees worked on together to make it easier to interpret the visual. The if-else. I keep reading that as I-felse. And it took me way too long to figure out that it was actually if-else. I was like, what is I-felse? It felt so dumb. Okay, anyway, the if-else function. This is what you use to assign one object or another depending on whether the first argument, which is test, is true or false. The arrow assigns values to variables. So here I'm making it to where project 1 and project 3 are given the values from the data set and then assigned colors. So make that. And then you have to replot it to be able to see the new one. Okay, so now we have employees that were on project 1 connected with green edges. Project 3 employees are connected with black edges. And those from project 2 are connected in orange. So this visual is going to tell us who worked on what together and makes that easier to interpret. But it doesn't give any information about who exactly turned over. So as you see, everybody's node is orange, so this isn't, like, it's informative, but it's not really like what we're trying to get to. So that being said, you can also color code the nodes based on characteristics of the employees. So obviously in this example, turnover is what we're going to want to look at here. The v parenthesis function is going to create a vertex sequence containing all of the vertices of a graph. And the vertex sequence is used as iGraph function arguments to like inform the visual. It's tied to the graph that it refers to. So here I'm specifying it to be tied to the employee network and then specifying the variables from that network here. So this is the variable that I want to look at. So, and then these are like the colors that it's going to be. So I'm specifying that red is going to be yes, they did turnover, and no, they're still here is going to be green. Okay. Replotting that. Okay, so now we have it to where we can actually see who turned over and what projects they worked on and how they're connected. So before I go into detail here, though, I'm going to create a legend to better explain what this visual is saying. It can be useful to create a legend to show what the color coding for the graph means, obviously, and for this, the legend function is going to be used. I think this would also be even more useful if I had way more people. So, like, I know that I'm using a small, super small, like, example, but if you had, like, a lot of people, I can see how this would be even more helpful. So running those. So there's going to be two legends. There's going to be legends for, see there it pops up. There's going to be legends for the colors here and legends for those. See? So now we can see that the names of people, we can see how they're connected in terms of projects they worked on together, and we can see whether they turned over or not. So basically, we're seeing that everyone that worked on Project 3 turned over. So I would say that this indicates that there was some kind of issue, whether it be solely work-related or task-related or possibly some social issues within this team. This looks to be the common denominator for turnover within this department. So this is going to provide the organization the information that they need to take the steps necessary to solve the issue and hopefully prevent it in the future. So, about describing the network. So visualizing the network is obviously useful for examining the data at a high level, but one of the most important features of social network analysis is the ability to mathematically describe a node's characteristics on the network. So the positions of nodes on the network are often described in terms of centrality. Centrally positioned individuals basically have a position of privilege over those relegated to the circumference of the network. So the three main types of centrality are degree, betweenness, and closeness. I'm going to go over degree and betweenness for the purpose of this example and because I think it's the most useful information for this particular example. So first we have degree centrality. The iGraph package has a function called degree to measure this. So then you specify what network you want, and you want to look at all of them. So here we have some actual like quantitative data. Degree centrality is the simplest of the three methods that I mentioned earlier. It just measures the number of connections between a node and all the other nodes. So looking at this output, Egger is connected to Williams and Salmons, so he should have a degree centrality score of 2. Sorry, I misspoke. Not looking at the output, but looking at this graphic. Egger should have a degree centrality score of 2, and we see that here. So that's reflected in the graph here. So Egger is connected to Salmons and Williams. So Salmons, on the other hand, has 6 lines on the visual, and this is reflected here in the data as the number 6. It looks like Salmons, Harrison, and Williams are pretty central to this network, and what's interesting is that all 3 of those people ended up turning over. So next we have closeness centrality. This is an evaluation of the proximity of a node to all the other nodes in a network, not only the nodes to which it's directly connected. This is defined by the inverse of the average length of the shortest paths to or from all the other nodes in the graph. Okay, I'm not going to lie, I read that one. So like, defined by the inverse of the average length of the shortest path. Okay, to or from all the nodes in the other graph. Okay, it will make more sense once I look at it, I think. Okay, yeah, so here's the output that describes closeness. So Harrison has the most closeness of all employees, connections to 6 other people on the team, and again, he turned over. Edgar, Nesbitt, and Connor, on the other hand, have the least degree of closeness, and they did not turn over. Interesting. See? This is interesting because it indicates that their interactions were with the other team members were likely more limited and less frequent. So, what does all of this information actually mean? It's basically telling us that there was something very, very wrong within the dynamics of this project team, particularly Project 3, that led to turnover. So the organization's next steps, which in real life I would outline in a project report, would be to design an intervention around teamwork or otherwise take this information to inform them on how to prevent the issue from happening again. So I might give them recommendations. So since these people are already gone, it might help to figure out what was it about the project that really set it off. Like what, aside from the social aspects, might have led to difficulties. Specifically, what was it about Project 3, other than the makeup of the team, that might have facilitated the challenges that led to turnover? So there is my organizational network analysis over.